Good afternoon. In the previous lesson we spoke about supervised learning, an approach where we had a clear plan, a textbook with answers in the form of labeled data, and a clear goal, teaching the model to predict those answers. But what happens in the real world? We rarely have ready-made answers. We have vast datasets, customer transactions, server event logs, medical records, user behavior on websites. And we want to understand what's happening there, what hidden patterns exist, what groups form, what anomalies appear. That is precisely what we will talk about today. We will dive into the world of unsupervised learning. In the course of our lecture we will get acquainted with the concept of unsupervised learning, study its key tasks, from clustering to association rule mining. We will compare popular algorithms and see how choosing one over another can drastically change the outcome. And then we will move on to the most important thing, the key challenges for a governance system. In the end, our goal is not merely to understand the risks, but to learn to manage them. We will consider several real-world practical cases and learn how to implement processes that allow us to harness the full power of unsupervised learning responsibly and safely. Let us begin. And, of course, as is tradition, at the end there will be a bonus quiz to test your acquired knowledge. So subscribe if you haven't already, so you don't miss the next lessons on the channel. Unsupervised learning is a class of machine learning methods that operate on unlabeled data. When we speak of unsupervised learning, the first thing to understand is why we resort to it. Imagine a huge dataset, whether it's website user behavior, financial transactions, or medical images. At first glance, it's just numbers and records, but within them lie deep patterns. Our primary task is to discover these hidden patterns. We want to see how individual elements relate to one another. Perhaps existing relationships will suggest new approaches to personalization, process optimization, or risk detection. Next, we must segment objects into natural clusters. Instead of manually assigning groups by arbitrary labels, we let the algorithm itself find homogeneous segments based on real behavior patterns, interaction frequency from one-off purchases to loyal subscribers, channels and time of activity, morning or evening users, online or offline. This approach allows us to uncover non-obvious groups, reveal hidden niches, and see the structure of our data in a new light. And finally, we search for anomalies, those outlier observations that may indicate failures, fraud, or, conversely, new opportunities. A single atypical case can lead to critical discoveries or help prevent serious problems. It is precisely the combination of these three scenarios, pattern discovery, segmentation, and anomaly detection, that makes unsupervised learning a powerful tool for exploring and managing data when we do not have ready-made answers to all our questions. Such a learning method is widely used in customer segmentation for targeted marketing campaigns, where algorithms find groups of similar behavior on their own. In the banking sector, these methods help detect suspicious transactions and prevent fraud. In IT monitoring, they reveal anomalies in logs, from bugs to attacks. And, finally, in recommender systems, they build connections between products, articles, or courses, offering users unexpected yet relevant suggestions. Before we dive deeper into this topic, I'd like to share a real-world example of using unsupervised learning algorithms and the potential risks and problems they can create. A large supermarket chain developed an algorithm that analyzed purchasing habits based on changes in consumer behavior. For instance, the algorithm tracked purchases of about 25 products, including certain vitamins, unscented lotions, hand sanitizers, and other items. It discovered that a particular group of women began buying these items alongside prenatal products. Having thus formed a group of potential customers, the supermarket started sending targeted ads. The most famous case occurred when a father of a teenage girl came into the store to complain that his underage daughter was being sent coupons for baby products and pregnancy-related items. He was outraged, believing the supermarket was encouraging teenage pregnancy. But a few days later the same father called back to apologize. It turned out that his daughter really was pregnant, but she hadn't yet told her parents. The algorithm had detected it before she confessed to her family. This case became the quintessential example of ethical issues in data analysis, questions of privacy, consent to data processing, and the potential social consequences of predictive analytics. And now let us consider the main tasks solved within unsupervised learning. Clustering, the division of objects into groups, clusters, so that objects within one group are as similar as possible to each other, and between groups as different as possible. Clustering is like a game of spot the difference, but in reverse. The algorithm looks not for differences but for similarities and groups objects accordingly. Imagine you have a city map with points marking your customers' homes. The method will find optimal locations for your stores so that each customer is as close as possible to one of them. Sounds logical, right? But here's the catch. The algorithm does not know about social boundaries, neighborhoods with varying incomes, historical features. It may suggest opening a luxury class store in an underprivileged area or, conversely, neglect entire communities. Dimensionality reduction, transforming data with many features into a more compact form without losing important information. This helps simplify analysis, visualization, and speed up training. Imagine describing a person with 10,000 characteristics, from eye color to music preferences. Dimensionality reduction methods say, let's describe the same person with just 10 characteristics, but in a way that preserves the important information. Principal component analysis is a classic example. It finds the most significant directions of variance in data, as if you look at a three-dimensional object and choose the best angle for a two-dimensional photograph to maximize the preservation of shape information. The problem is that these principal components are often impossible to interpret. A principal component may turn out to be a strange combination of age, income, and number of purchases. But how do you explain to a regulator or a client why this combination is important? Association rule mining, discovering patterns of the form, if A occurs, then B often occurs. This is not prediction, but the detection of recurring dependencies between events. The classic example is beer and diapers. What could these disparate product categories have in common? In the 1990s, an American retail chain found that on Thursday and Friday evenings men often bought beer and diapers together. The logic was simple: young fathers went to the store for diapers for their baby and grabbed beer for the weekend. Stores began to place beer next to baby products, and sales increased. But what if such analysis reveals more sensitive associations? What if the algorithm finds a link between purchasing certain medications and other products, thus revealing medical information? Or between products and political preferences? Anomaly detection, the identification of objects that differ markedly from the rest. Such anomalies can indicate errors, malfunctions, or suspicious behavior. Anomaly detection is about finding what doesn't fit the general pattern. In cybersecurity it could be suspicious traffic, in medicine unusual patient indicators, in finance suspicious transactions. Sounds useful, but here's the nuance. What is an anomaly? It depends on what the algorithm considers normal. And normal is defined by what appears most frequently in the data. Imagine an algorithm that analyzes resumes for HR. If the data contains more resumes of male programmers, then a resume of a female programmer may be classified as anomalous, not because anything is wrong with it, but simply because it differs from the typical. Colleagues, let us talk about metrics. And an immediate important caveat: this part of the lesson is not meant to turn you into data scientists. Your task as AI governance specialists is to understand what lies behind the numbers your technical team provides. Metrics in unsupervised learning are your shield before regulators and stakeholders. When a regulator asks, "On what basis did you group customers this way?" you must have an objective answer. Let us break down what the main metrics mean from an AI governance perspective. Silhouette score is a measure of how clearly clusters are separated. Values range from -1 to +1. A score of, say, 0.7 means that clusters are well separated. For us, this is good news. It will be easier to explain the grouping logic to a regulator or client. But here too there can be a trap. An excellent silhouette score can occur when grouping people by race, gender, and other protected characteristics. The algorithm doesn't know that's unethical. To it, these are just clear, well-separated groups. The Davies-Bolden index measures cluster compactness. A low index helps choose the optimal number of clusters, which is important for documenting decisions. But it doesn't account for the business meaning of the resulting groups. In anomaly detection we face the classic dilemma. Precision at K and recall at K, the balance between security and fairness. High precision means fewer false positives, fewer blocked operations of honest customers, fewer complaints. High recall means we catch more real problems, fraud, anomalies, but we also block more operations. The social risk lies in the fact that these metrics can perform differently for different population groups. In dimensionality reduction we use the reconstruction error. This metric measures how accurately the model reconstructs the original data after compression or transformation. It is computed as the difference between original data and its reconstruction. A high reconstruction error indicates significant information loss, which can reduce the reliability and interpretability of model conclusions. I want to draw your attention to one non-obvious danger. The algorithm may preserve technically significant details, such as numerical patterns, but lose socially important nuances, for example cultural or demographic features, creating risks for the ethical application and governance of AI. Now that we understand what tasks unsupervised learning solves, let us look into the toolbox. You do not need to be an expert in every algorithm, but knowing that different approaches exist will help you have more productive dialogues with the technical team. Let us start with the most popular algorithm, K-means. Imagine you plan to open a chain of coffee shops in a city. You have data on where potential customers live, and you want to find optimal locations for 5 coffee shops so that each customer is as close as possible to one of them. The K-means algorithm works just like that. The algorithm randomly places 5 points on the map, centroids, then assigns each customer to the nearest point. After that it recalculates each group center and moves the centroids there. This process repeats until the centroids no longer move. The density-based spatial clustering algorithm, DBSCAN, simpler to understand for noisy applications, works on the principle of density. Imagine analyzing a crowd of people from a bird's-eye view. DBSCAN finds dense clusters of people, names them clusters, and classifies solitary people as noise. The algorithm works like this. It takes each point and checks whether there are enough neighbors within a given radius. If yes, the point becomes a core of a cluster and all neighbors join the cluster. If a point has few neighbors but is near a core, it also falls into the cluster. If a point is isolated, it becomes an outlier, noise. The advantages are obvious. The algorithm does not require specifying the number of clusters in advance, can find clusters of arbitrary shape, and is robust to outliers. Hierarchical clustering creates not just groups, but a whole story of group formation. Imagine an inverted family tree. At the bottom you have individual points, and as you move up they merge into families, tribes, clans. 2 approaches exist: agglomerative, bottom-up, start with each point as a separate cluster, then sequentially merge the most similar clusters until all merge into one, or divisive, top-down, start with one large cluster containing all points, then sequentially split it into smaller ones until each point becomes its own cluster. The main advantage is full traceability of decisions. A dendrogram shows how clusters formed. You can explain to stakeholders, clients A and B merged into the same group at step 3 because their profiles were the most similar among all remaining pairs. Colleagues, it is very important to understand that the goal of our course is not to deeply study all tools and methods of machine learning artificial intelligence, especially at this stage. Our goal is to get a general idea of technical tools and, most importantly, understand how exactly they impact our subject, AI governance and regulation. Now imagine that you must explain to a regulator or client why data were analyzed by K-means, and not, for example, DBSCAN. Each algorithm can give different results on the same data. A telling case occurred in an insurance company where different departments used different algorithms to cluster and segment the same clients. The marketing department used K-means, the risk department DBSCAN, and the sales department hierarchical clustering. As a result, the same client was simultaneously considered premium, high risk, and standard. Chaos in decision-making was inevitable. Now that we understand how these algorithms work, let us figure out why they create such headaches for governance and compliance specialists. The first and main problem is interpretability. In supervised learning we can say, the algorithm classified this image as a cat because it saw whiskers, pointed ears, and a certain shape of eyes. Not perfect, but at least something. In unsupervised learning explanations sound more like, the algorithm placed this customer in cluster number 3 because their profile is similar to other members of this cluster by a combination of 847 different factors that we cannot fully interpret. Try explaining that to a regulator or client who demands to know why they were denied a loan based on cluster analysis. The second problem is even more insidious. Supervised learning algorithms can be biased if the training data are biased. But unsupervised learning algorithms can create biases from seemingly neutral data. Take a natural language processing algorithm that analyzes texts and creates vector representations of words. If it learns from texts where the word programmer more often occurs near male names, and nurse near female names, the algorithm will encode these gender stereotypes. When we later use these embeddings for resume clustering or job recommendations, biases will appear. The algorithm will recommend technical positions to men and caregiving positions to women, even if we never specified gender as a variable. The third problem concerns privacy. Unsupervised learning algorithms can infer sensitive information from seemingly innocuous data. A classic example, an online movie platform provided anonymized movie rating data for a recommendation system improvement contest. Researchers were able to de-anonymize users by matching the data with public IMDb ratings. They discovered not only people's movie preferences, but also their political views, sexual orientation, and other personal information. Clustering and association rule mining algorithms can build detailed profiles of people far more accurately and completely than what users are willing to disclose voluntarily. So, what should we do? How to govern systems that by definition do unexpected things? The precautionary principle in action. Rule number 1, always assume that your unsupervised learning algorithm will find something unexpected, and that something may prove problematic. Before you run customer clustering, ask yourself, what if one of the clusters correlates with protected attributes? What if the algorithm finds a way to distinguish people by characteristics we consider unethical? Conduct a preliminary data analysis. Which variables correlate with protected characteristics? Which combinations of variables can serve as proxies for sensitive information? Since unsupervised learning has no single quality criterion, use multiple validation approaches. Technical validation, cluster stability when parameters change, interpretability of principal components, statistical significance of association rules. Expert validation, involve domain experts to interpret results. If the algorithm grouped a cluster of bank clients, can a credit specialist explain why these clients are clustered together? Social validation, how are algorithm results perceived by stakeholders? If medical data clustering highlights a group of patients, how do the patients themselves and the medical community perceive it? Continuous monitoring. Unsupervised learning algorithms are especially sensitive to data changes. Clusters that made sense before may become obsolete or even harmful today. Implement data drift monitoring systems, track how clustering results change over time, what new patterns emerge, what old ones disappear. It is especially important to monitor fairness of results. If a year ago your clusters did not correlate with protected attributes, that does not guarantee it will remain so today. Friends, here is our bonus quiz on the material from this lesson. 6 questions to help test how well you have absorbed the key ideas about unsupervised learning and its risks. What is the key feature of unsupervised learning? What is the main ethical question when predictive algorithms based on purchasing behavior draw conclusions about sensitive information? How can an anomaly detection algorithm analyzing resumes lead to systemic bias? Why is the choice of a specific clustering algorithm an important issue for AI governance? What is the black box problem in the context of unsupervised learning? Which of the listed approaches is not a typical method for validating results in unsupervised learning, especially from an AI governance perspective? Please pause the video and independently answer each of these 6 questions. Write your answers in the comments under this video. It will be interesting to discuss which points you found most challenging or important. Please give this lesson a like and subscribe if you found it useful and don't want to miss the next materials on AI governance. Correct answers and detailed explanations, as always, will appear in our Telegram channel. The link is in the description. Friends, unsupervised learning is simultaneously a powerful tool and a serious challenge for governance systems. These algorithms can find surprising, non-obvious insights in data, but they can also create unexpected problems. The key to successful governance is embracing uncertainty. We cannot fully predict what an unsupervised learning algorithm will find, but we can prepare for surprises. Foster a culture of responsible AI in your organizations. Train teams to think not only about technical efficiency, but also about social consequences. Implement processes for ethical evaluation of algorithm results. And remember, the goal of a governance system is not to halt innovation, but to channel it in a way that benefits society. Unsupervised learning can become a powerful force for good if we learn to govern it properly. See you in the next lecture.